You are adding and subtracting decimals in this warm-up. We have 5.6, put a 0 there so we can line up those decimal places. Then 4.72. 0 plus 2 is 2. 6 plus 7 is 13. 5 plus 1 plus 4 is 10. And that decimal stays right in line there. For subtraction, we have 4.1 and 2.86. In this gap, we're going to stick a 0. We're subtracting. 10 minus 6 is 4. 10 minus 8 is 2. 3 minus 2 is 1. Complete the remaining problems. It says you are planning a trip to Mars. What will you take with you and why? I would include some oxygen, some water, some food, just like they did. I would also bring some clothes, and a shelter, and maybe some games to keep me from getting bored. The first three things are to survive. The oxygen, the water, the food, and the clothes and shelter too are going to keep me warm because Mars is farther away from Earth. And then the games to keep me busy, especially if I'm going alone. To communicate with people on Earth, you need to send radio signals that travel between Earth and Mars at the speed of light. What do you notice about the orbits of Earth and Mars? So we saw in the first video clip that in some parts of their orbit, they're very close to each other. Not very close, but closer to each other. And in other parts, they're farther away. You might also notice that those orbits are not circles, and they're actually called ellipses, or elliptical orbits. Oh. Here it says, which information do you need to know to find out how long it will take your message to reach Earth? Select all that apply. We don't need to know about their breathing. The distance between Earth and Mars is definitely important. This one is the closest, and down here we have the farthest distance. It also said in this slide that it travels at a speed of light. So we're going to want to know how much the speed of light is. We don't need to know about their water intake, the weights, the food, or the space shuttle at this point in time. It says the closest distance from Earth to Mars is about 34.8 million miles. The speed of light is about 186,000 miles per second. How many minutes does it take your message to get from Mars to Earth? When the two planets are as close as possible, round your answer to the nearest hundredth. So we can write 34.8 million as 3, 4, and then we've got 6 place values after it. And we are going to divide to figure out how many seconds it would take, and then we'll convert it to minutes after. But I don't want to divide by 186,000. Just like we could move the decimal to the right, we can also move it to the left. So I'm going to move it 3 spots to the left. That way I'm dividing by 186 rather than 186,000. So over here I have 34800 divided by 186. So I know it fits in there one time. 8 minus 6 is 2. 14 minus 8 is 6. 2 minus 1 is 1. Bring down a 0. I like to write down a list of multiples of 186 to help me. So it fits into 1,620. 1, 2, 3, 4, 5, 6, 7, 8 times. Ten minus 8 is 2. 11 minus 8 is 3. 5 minus 4 is 1. Bring down another 0. That fits in 1, 2, 3, 4, 5, 6, 7 times. 10 minus 2 is 8. 1 minus 0 is 1. 3 minus 3 is 0. 1 minus 1 is 0. We can use a decimal. It doesn't fit into 180, but it does fit into 1,800. That is 9 times. And this should be enough for us to approximate. This is the seconds. Now we want to change it into minutes. So we're going to convert the seconds into the minutes by dividing 187.09 by 60, because there's 60 seconds in a minute. So 60 fits into 180 3 times, or 187 3 times. Bring down the 0. 60 fits into 71 time. And 109 1 time as well. I guess we should probably continue this one more place value so we know if we need to round up or if it can stay. So let's see. 1,800 minus 1,674 is 126. And then it fits into 1,260. 1, 2, 3, 4, 5, 6 times. So it fits into 496. Let's see. 60, 120, 180, 240, 300, 360, 420, 480, So the 8 rounds it up to a 2. So it should say 3.12 minutes. And we got the smiley face, so we know it arrived. For this one, same kind of process, but instead of 38.4 million, we now have 250 million. So we're going to get rid of some place values here. We are dividing 250,000 by 186. All right, so with that list of the multiples of 186, it can fit into 250 one time, $640, it can fit in there 3 times. $13 minus 5 is 8. It fits into 820 4 times. $11 minus 4 is 7. Fits into 764 times. Fits into 160 times. Or 1,600, it could fit in there 8 times. So let's start there. We have 1344.08 divided by 60. 60 fits into 130 twice, leaving us with 14. Bring down the 4, fits into there twice. 4 and a 2. Bring down the 0, fits into 240. What is that? 4 times. Bring down the 8, fits in there 0 times. If we keep going, it would only fit in there 1 time. So it's going to round to 22.4. Yes, 22.4 minutes. Suppose Mars is at the farthest distance from Earth. You send a message to a person on Earth. How many minutes does it take to receive a reply if the person responds immediately? Explain. It should take 22.4 minutes to respond or to receive the response. And if the change of the orbit had any impact in those matters of minutes, then it would be less because it would be at the farthest distance when you sent it. So then it should be closer. So it should take 22.4 minutes or less to receive the response. At this rate, how many messages could you receive in 12 hours? Ooh, so 12 hours. 12 times 60. 2 times 6 is 12. 6 times 1 is 6, plus 1 more makes 7, so 720 minutes divided by about 22. We could fit 3 would be 66. 12 minus 6 is 6. Bring down the 0. 22 would fit in there about not 4 times. 2 times. Not 22. Come on, Mrs. Stocks. 44. And then let's see. 22 goes into 160. That'd be 20, 40, 60, 80, 100, 120, 140, about 7 times. Would give you 154. So about 32 messages that you could send back and forth. 32 or 33. Oops. Okay. On Mars, you need food, water, and oxygen to survive. Which information do you need to know to determine how much of each resource you need to survive? Well, we would need to know how much oxygen. We would need to know how much food and how much water. You might also need to know the conversions to figure out how much weight it would be, but right now we're just trying to figure out how much of each resource, so the units don't really matter. An astronaut breathes 613.2 kilograms of oxygen in 2 years. You will need supplies to live on Mars. Let's estimate that it takes 2 years for the space shuttle to go to Earth, gather supplies, and then come back to Mars. How many kilograms of oxygen do you need to live for 1 day? Round your answer to the nearest hundredth. Well, there are 365 days in a year, and we have 2 years. That's 10, 12, 13, 6, 730 days. So we're going to divide 613.2 by 730. I'm going to move the decimal to the left 1 spot so that I'm working with 73 instead of 730. And I'm working with 61.32 instead of 613. All right, so 73 doesn't fit into 61, but it does fit into 613. Again, I'm going to create that list on the side just as a guide. All right, so it fits into 613. What is that, 8 times? 13 minus 4 is 9. 10 minus 8 is 2. Bring down the 2. Fits into 292. 1, 2, 3, 4 times exactly. So then we will type that in there. 0.84. It does say to round to the hundreds, and we're already in the hundreds. And we got the check mark, so we're good to go. An astronaut needs about 25.9 liters of water each week to survive. There are 52 weeks in 1 year. What is the least amount of water in liters you need to bring to Mars to survive for 2 years until the space shuttle returns? Round to the nearest tenth. Well, in 1 year, there's 52 weeks. So in 2 years, that would be 104 weeks. And we're drinking this much water per week. So we've got 250 or 25.9 times 104. 4 times 9 is 36. 4 times 5 is 20. Plus 3 is 23. 4 times 2 is 8. Plus 2 more makes 10. put in your place value spacer, well then that's going to be 0, 0, and 0. This time you're going to need 2 place value spacers. 1 times 9 is 9, 1 times 5 is 5, 1 times 2 is 2. Add those up. 6, 3, 9, 6, and a 2. We have 1 decimal place in our question, so we need a 1 in our answer. And we're going to try 2,693.6. Yes. An astronaut eats about 1.27 pounds of food for each meal. Assume you eat exactly 3 meals a day. So let's start there to figure out how many pounds they eat per day. 3 times 7 is 21. 3 times 2 is 6, plus 2 more makes 8. 3 times 1 is 3. We have 2 decimal places in our answer, so 2 question and our answer. Then it says that you need to survive for 2 years. We already said that there were 730 days in 2 years, so we're going to do 730 times the amount that we eat per day. 1 times 0 is 0. 1 times 3 is 3. 1 times 7 is 7. Put in that spacer. 8 times 0 is 0. 8 times 3 is 24. 8 times 7, is 56, plus 2 more makes 58. We need 2 place value spacers. 3 times 0 is 0. 3 times 3 is 9. 3 times 7 is 21. We've got 0, 3, 11, 18, 7, and a 2. We've got 1, 2 decimal spots. 1, 2 decimal spots. It says to round to the tenths. So this would be 2781.3. Yep. You will need 613.2 kilograms of oxygen, 2,693.6 liters of water, and 2,781.3 pounds of food for 2 years. What calculations do you need to make before you can find the total mass in kilograms of a 2-year supply of food, water, and oxygen? Explain. We need to convert the liters of water to kilograms and the pounds of food to kilograms. So they are all in the same unit. The reason they have to be in the same unit is so that we can add them all together. Okay, so what is the total mass in kilograms of a 2-year supply of food, water, and oxygen? Round to the nearest hundredth. So we already have kilograms of oxygen. The liters, it's a 1 liter is 1 kilogram, so this is just kilograms. So 1 to 1, so we can just write it as kilograms. But the pounds we do need to convert. So we're going to multiply 2,781.3 by 0.45. So 2,781.3 times 0.45. 5 times 3 is 15. 5 times 1 is 5. 5 times 8 is 40. 5 times 7 is 35, plus 4 more makes 39. 5 times 2 is 10, plus 3 is 13. 4 times, oh, we need our spacer here. 4 times 3 is 12. 4 times 1 is 4, plus 1 more makes 5. 4 times 8 is 32. 4 times 7 is 28, plus 3 is 31. 4 times 2 is 8, plus 3 more makes 11. So that's 5, 7, 5, 11, 5, 2, and a 1. We've got 1, 2, 3 spots. We're going to round that to the hundredths so that 5 makes the 7 change to an 8. So I have 1251.58 for our food. I have 2693.6. We can put a 0 here for our water, and 613.2. We can put a 0 there for our oxygen. 8 plus 0 plus 0 is 8. 5 plus 6 is 11, plus 2 more makes 13. Line up our decimal there. 3 plus 3 is 6, plus 1 is 7, plus 1 is 8. 9 plus 1 is 10, plus 5 more makes 15. 6 and 6 is 12, 13, 14, 15. 1 plus 1 plus 2 is 4. Uh-oh, I've got an error here. This should be 5 times 3 is 15. 5 times 1 is 5, plus 1 more makes a 6. So that should have been an 8, which would round that up to a 9. And this 9 goes there. Okay, now we should be set. Suppose it costs about 20,000 to send 1 kilogram into space. How much will it cost to send a 2-year supply of food, water, and oxygen for 1 person? Okay, so we had on this last slide 4,558.39 kilograms, and we are multiplying it by 2,000. Instead of multiplying by 20,000, because it's just going to be a bunch of rows of 0, I'm going to multiply by 2, and then I'm going to move my decimal 1, 2, 3, 4 extra places at the end. So we're going to multiply by 2. 2 times 9 is 18. 2 times 3 is 6, plus 1 more is 7. 2 times 8 is 16. 2 times 5 is 10, plus 1 more is 11. 2 times 5 is 10, plus 1 more is 11. 2 times 4 is 8, plus 1 more is 9. And I have 1, 2 place values here, so I should have this. But then since it was 20,000 and not 2, I'm going to move my decimal 1, 2, 3, 4 places towards the right. So it should be 911,678 with 2 zeros after it. Oops. So that is, let's see, if we were to put our commas in here, that's $91,167,800. That is an expensive trip to space. Okay, what do you wonder about the cost of sending supplies to a colony on Mars? Well, I wonder if that is a realistic amount for a 2-year trip with 1 person. Are these numbers based on how expensive it is to send people to space in 2024? 2025, back when it was first possible to send people into space? Can we send people to Mars? I wonder a lot of things about space. Let's see, what else? What do you wonder about the cost of sending supplies to a colony on Mars? Well, this was to survive, but it wasn't necessarily to thrive. How much would it cost to send additional supplies, such as games or extra clothing, what problems do you think could occur with planning exactly this much food, water, and oxygen for 2 years? Well, what would happen if you spilled some water or burn your food? Is there enough extra to survive? Let's see what else. Maybe there's a surplus. Maybe we have too much. What if we got stuck for longer than 2 years? What other options could there be for resupplying food, water, and oxygen? Explain. Well, maybe we could try to create a greenhouse or have our food freeze dried so the food doesn't take up as much space. So we can put more. Maybe the ship that goes to Mars is manned by a robot instead of a person, so they don't have to eat food as they're traveling. There's all kinds of different things we could think about. All right. Make sure that your workbook is filled in with the multiplication and the division. All the stuff that you had to write down to find your answer should be in your workbook.